Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 6, Integration and Accumulation of Change. Today's topic is 6.2, where we're talking about approximating areas with Riemann sums. Enjoy today's notes.
All right, welcome to 6.2 Approximating Areas with Riemann Sums. In the last lesson, 6.1, we talked about how to find the area under the curve of really nice, clean geometric shapes. We're talking about like rectangles and triangles and trapezoids and semicircles, all of which are useful for the AP exam. Today we're going to try to figure out how do we approximate areas under curves that are not so nice, right? If I wanted to find the area under this curve, we can't make nice geometric shapes that are like neatly exact. And so we have this idea of what we call a Riemann sum, which is a way to estimate the area or approximate the area under a curve when you can't find the exact value because you don't get those nice clean geometric shapes. So the graph of the function g of x is shown to the right. Approximate the area under the curve on the interval from 2 to 6 with n subintervals by using a left rectangular approximation method. So first off, what I'm going to do is I'm going to just identify the x values that we're looking at. We're talking about the area from 2 to 6. So I'm talking about this area under this curve between those two x values that we've got right here. Now, when we talk about what's called the left rectangular approximation method, we're talking about the idea here that, okay, again, I can't like say that this is a triangle, right? If I drew a trapezoid, if I do that, then it's not going to be exact. So throughout the years, people came up with different ways of trying to estimate that area under the curve. And one of them is by using a series of rectangles that are getting smaller and smaller and smaller and smaller and smaller. So if we say, for example, n subintervals, so we're talking about how many rectangles are there under that curve in that area. So n in this case is the number of rectangles. It's the number of rectangles that we're talking about. And I'm going to give some visualizations of what this might look like. So in this case, if we talk about n equals 1, well, in this case, what would the width, my question first off is what would the width of that rectangle be? Well, we're going here in this problem from 2 to 6. So in this case, we're taking the 6 minus the 2, and then we have, that's going to give us that it's going to be 4 units long. And so if I were to draw this rectangle, here's what it would look like. It would look like this. And actually, let me change up the color just so it's clear. So here's what my rectangle would look like if I had just one rectangle going across. So this would be a rectangle with width of 4 going from 2 to 6, and we would have just one rectangle here. Now, why is this called the left rectangular approximation method? Notice for my rectangle that the left side of my rectangle, specifically right here, is the part that's touching the curve. So this spot right here is the part where it's touching the curve. The right side of my rectangle is not touching the curve at all. In this case, it's significantly below it. Now again, what are we trying to do? We're trying to estimate the area under the curve for this function. So in this case, this rectangle is sort of a terrible estimate of it, right? There's all this area up here that's missing if we're talking about the area between the curve and this x-axis. So what do we do? Well, in this case, what we can do is we can try to add some more rectangles. We're going to increase our n. So in this case, what would the width of each rectangle be if we have 2 rectangles? Well, we're still going from 6 minus 2. We're still going 4 units. But in this case, I'm going to divide that in half because we've got these 2 rectangles. So I have 4 divided by 2. That's going to tell me that the width needs to be 2 units wide when I'm drawing my rectangles here. So I'm going to actually erase what we've got here. If I'm doing this that's then 2 units wide, here's what this would look like. We would have one rectangle here at 2, one rectangle starting at 4, and again, I'm going to use the left side of these. So here's the width of this first rectangle. The left side is the part that needs to be touching the curve. So I'm going to draw my the top of my rectangle going across. So this is rectangle 1. And then my second rectangle is going to go from 4 to 6, but again, the left side is the part that needs to be touching the curve. So I'm going to go straight across right here and this would be my second rectangle. Now this is a slightly better estimate because the previous one went straight across here, so this now has a little bit more area that's going into this part that's missing, but it's still not a fantastic estimate because we're missing this part here and this part here if we're trying to find that exact area under the curve. So what do? Well, we can increase the number of rectangles. Let's try n equals 4. Let's double it up. Well, what would the width of each one be? Well, we're going from 6 to 2, so 6 minus 2, and we're splitting that into 4 rectangles. So 4 over 4 means that the width needs to be 1. So if we erase, I'm going to erase and just sort of start over for this. We've got, again, we're going all the way up to 6, so I'm going to stop there. I'll actually put both those lines. We're only doing between x equals 2 and x equals 6. But in this case, we're saying the width needs to be 1. So I'm going to draw vertical lines in increments of 1 going up to the curve. And our first rectangle is going from 2 to 3. And the left side is the part that needs to be touching the curve. So I'll go across right there. That's my first rectangle. My next rectangle is going from 3 to 4. The left side is the part that needs to be touching the curve. So I'm going to go straight across right there. There's my second rectangle. The next rectangle is going from 4 to 5. And the left side of it is the part that's touching the curve. So we're going to go across right there. That's my third rectangle. And then here my last one's going from 5 to 6. And the left side is the part that's touching the curve. So we're going to go across right there and have our final rectangle. What you might notice in this case is that as we add more rectangles, there ends up being less and less missed area here. As we've increased the rectangles, this is getting a little bit more accurate. So some highlights of this that I want to emphasize. If we're talking about the width, how wide should these rectangles be? You'll notice this pattern that I had over here, where I was taking the subinterval that they gave me, subtracting that, and then dividing by the number of rectangles. In general, if we're talking about going from A to B with n rectangles, the formula is going to be b minus a over n. That is going to be the formula for the width of a rectangle if you're using this method. Additionally, we just said something that's really important that I don't want you to miss, and that is the fact that what happened as we increased the number of rectangles? It gave us a better estimate. And this is definitely true for Riemann sums overall. The more rectangles, so I'm going to put this huge up here, the more rectangles, aka the larger n gets, the better the estimate. So it's a better estimate. Now the idea here is this, right? Like as we have more of these, less of this area is going to be sort of like wasted and missed here. But it's never going to be exact, right? Because we have these like horizontal lines and there's going to always be some area missed. So in general, the more rectangles that you have, you know, it's a better thing, but it's going to always end up being an approximation or an estimate of that area under the curve until we can bring in some more calculus, which we'll talk about in the next couple lessons. But this idea, this approximation method of using these rectangles under the curve is what's called a Riemann sum. So that's the title of today's notes, a Riemann sum. And so that's what we've got here. It was named after a German mathematician named Bernhard Riemann. And I'm hoping that I'm pronouncing that correct, but I think it's Bernhard Riemann. Maybe let me know if you find out otherwise. The idea here, again, with this Riemann sum is that we're adding up a bunch of rectangles to approximate the area under a curve. And so that is like really the big idea of this like Riemann sum. Let's move on. So below is the graph of f of x is equal to 4x minus 1/2 x squared. Use Riemann sums to find the approximation of the area under the curve. So Riemann and Riemann sums, you'll notice that in this particular problem, we emphasized that we were talking about left rectangles. This is not the only way to do it. In fact, you'll notice here that we've got sort of two different ways, a left Riemann sum and a right Riemann sum. The difference between the two of these is all about which side of the rectangle touches the curve. So which side of the rectangle touches the curve? If they say left, then it's the left side of the rectangle. If they say right, then it's the right side of the rectangle. And so in this case, let's take a look at what we've got. We see here that we're going from 2 to 8. So from 2 to 8, I'll just sort of draw these like red lines to emphasize where we're looking. So 2 is there. 8 is here, so that's where the curve is, and we're trying to find this area that's between the curve and the x-axis, so the area under the curve. If we're doing 3 subintervals, remember the way that we said that the width is going to be by subtracting the interval, so 8 minus 2, and then we're going to divide by the number of rectangles, so 3. So 8 minus 2 is 6, 6 divided by 3 is 2. That is going to be our width of each rectangle. What I'm going to do then is I'm going to draw vertical lines every 2 units. So from 2, I'm going to go 2 units over. I'm going to draw a vertical line up to my curve. I'm going to then go 2 more units over. I'm going to draw a vertical line going up to my curve, and I'm going to stop. So our left Riemann sum is going to be the left side of this. Here's the base of my first rectangle. The left side of it is where the top of that curve is going to be. That's the first one. The second rectangle, the base is going from 4 to 6, and we're going to use the left side. Well, something interesting happens here. I actually need to go across over the curve a little bit here. So that rectangle is going to be slightly larger than that area. Interesting. And then my third one, going from 6 to 8, if we go to the left side, looks like it's going to be about right there. This one is also going over the curve a little bit. So maybe the idea here is that, if we find these 3 rectangles, this one underestimates the area a little bit. These 2 are over, so maybe it'll cancel out and it'll give us something that's pretty close. The idea that we had said before about more rectangles being better is also true here. Even if there are some below and some above, if I increased the n value here, if I had did like 100 rectangles or 1,000 rectangles, it would give me a very, very accurate and precise amount of area between the curve and the x-axis. But in this case, like, how do we calculate this? In this previous problem, I guess we didn't actually find the area here, but they're asking us here to like find an approximation of the actual area. Don't just draw it. Let's actually do it. So I'm going to erase this width calculation. Hopefully you remember how we did that. And let's talk about what we notice. So what I notice first for this first rectangle that we've got right here is that the width of that rectangle is in fact 2 units. But how tall is that rectangle? Well, that rectangle to me looks like it's at about a height of 6. And that's fine for these first 2, but if I'm getting like over here for this rectangle, how do you know how tall that is? Well, in this case, they gave us actually the formula for the graph, the height of the function, and we're going to use that to our advantage. In fact, so our first rectangle that we've got right here is going from, it's 2 units wide, and it's whatever the height of this line is at x equals 2, right? Because the rectangle was built going up to the curve on the left side of it. So it's going to be whatever 2, the width is, times the height of the function, so f of the value when x is equal to 2. So it's 2 times f of 2. Maybe it's 6, maybe it's not. The only way that I could be sure, based on, not just estimating from the graph, would be to actually plug into the function and find out what that is. The next rectangle that we've got, I'll change up the colors, we see also has a width of 2, and the height is based on the left side of it, which is the height of the function when x is equal to 4. So the next rectangle's height is going to be 2 times whatever the height of the function is when x is equal to 4. So that would be f of 4. In our third one, we see that the width is 2, and again, the left side determines the height of this rectangle. So it's going to be whatever the height is when x is equal to 6. So 2 times f of 6. Now in this case, to find these precise values, we're going to want to plug into our calculators to find these actual values. For the sake of time, I'm going to just sort of skip ahead and just say that this is in fact a height of 6 at x equals 2. It is a height of 8 when x is equal to 4, and it is in fact this picture is slightly off, but it is a height of 6 when the function, the height of the function at x equals 6. So that is going to give us 12 plus 16 plus another 12. This is going to be about 40 units, 40 units squared if we're talking about the area under the curve. They didn't give us any actual units on the x and y axis, so there's nothing I can be more precise with in terms of this. But my estimate in this case would be 40 units squared. And yeah, maybe, my guess just looking at this is maybe this is a little bit over what the actual area is, because it looks like there's more area here that's outside of this curve than there is being missed here. But what happens if we do the right Riemann sums? So same idea, we're going from 2 to 8 and we're doing 3 subintervals. So if we draw our vertical lines at 2, and it's finishing at 8, so I'm not going to draw a vertical line since it's at the x-axis at 8. We would also want to have widths of 2 units. So in this case, I'm going to draw those vertical lines. Here's my first vertical line at 4, then my one at 6, and then technically I'm drawing a vertical line here at 8, but it has no height because the function is at 0 there. Now for our first rectangle, I guess we'll go back to colors. All right, so we've got these 3 rectangles that we're going to need. The first rectangle is going from 2 to 4. Now, in this case, if we're using the right Riemann sum, that means the right side of this rectangle is what's defining the height of this. So I'm going to go start here, and the height of the function is going to go this way. So notice that this rectangle is different from the one over here, even though these were the same function, right? This is the exact same function, but now this rectangle ends up being bigger in this case because we use the right side of the rectangle to touch the curve and not the left. This, the left side touched, here the right side touched. If we go to our second rectangle, our right side is touching right there, and so we can go straight across. That would be our second rectangle that we've got there. And then our third one, the right side is going to be touching here at this graph. So it actually has, I'm going to just draw sort of a line here to represent this. This is a line with height 0. So it's a rectangle with height 0. Because the right side of this, it has a height of 0. And so we don't actually end up drawing a rectangle for it. There's a rectangle with no area there, and I'm just sort of drawing this line as a placeholder. So how would we calculate the area? So in this case, each of these, again, has a width of 2, right? Each of these has a width of 2. So we're going to have 2 times the height of this rectangle, which is based on the right side. So whatever the function height is at x equals 4, so 2 times f of 4, plus this next rectangle, the second rectangle, is the height is based on the height of the function at 6, so 2 times f of 6, plus 2 times the height of the function at 8, which looks like it's 0, but let's be sure, so 2 times f of 8. Again, we would want to use our calculator to do this, but ultimately this is going to be, 2 times 8 plus 2 times 6 plus 2 times. F of 8 does in fact end up being 0, and so the area under this curve, this estimate, is going to be about 28 units squared. So we have the same exact curve, right, in 2 different cases here. One where we did a left Riemann sum, one where we did a right Riemann sum, and we got these 2 values of 40 units and 28 units. So here maybe we were a little bit over. Here maybe we were missing a bunch of area, right? I didn't get this area or this area over here. And so really to me, this sort of just tells me that the area is somewhere between these 2 values. It's got to be between 28 and 40. I don't know, is it closer to 1? Is it exactly in the middle? I'm not sure, but it's going to be somewhere between these 2 values. Nice. Now, those are not the only ways that we do Riemann sums. In addition, there are 2 other ways that you can do Riemann sums. The first is what's called a midpoint Riemann sum. This is another rectangle method, and then the other is using trapezoids. So we're going to talk about both of those. Both of these are also fair game on the AP exam, so sometimes left Riemann sums come up, sometimes right Riemann sums come up, sometimes midpoints, sometimes trapezoids. So we really have these 4 ways of estimating under the curve. Let's take a look at these other 2. So same exact graphs as before, right? Same exact ones that we were doing with these two. Except I want you to see this exact same function using these different methods. So once again, we're going to go from 2 to 8. So that area under the curve is what we're trying to estimate between x equals 2 and x equals 8, because they told us that way back when, all the way here, and they told us that here as well. Our width is still going to be, again, the way that you calculate the width of these is true for midpoints and trapezoids as well. The width is going to be b minus a over n. So that's going to be 8 minus 2 over 3. So that's 6 over 3, which is going to be equal to 2. So I'm going to draw my vertical lines. Do I want those vertical lines? Yeah, I do. I'll draw my vertical lines to separate this into increments of 2. And so what we see is we've got the first rectangle, we've got the second rectangle, we've got the third rectangle. Now, why is this called a midpoint Riemann sum? Well, the left side of the rectangle was if we did a left Riemann sum, the left side touched it. If we did a right Riemann sum, the right side touched it. If we're talking about the midpoint, we're going to imagine the x value that's exactly between the left and the right. So in this case, 3, and we're going to go up to that value, and that's going to be the height of our rectangle. So that looks like that is about right here. So we went all the way up. Midpoint between 2 and 4 is 3, and then we're going to draw the height of our rectangle there. So this would be our first rectangle. Notice here in this case that neither the left side of the curve of the rectangle or the right side of the rectangle touch the curve. It is the midpoint of that rectangle that is determining the height. Same story for going from 4 to 6. If I want to visualize, halfway between 4 and 6 is 5. So I'm going to go up here to 5, and I'm going to draw my midpoint line going straight across and draw my rectangles going down. That would be my second rectangle for this. For my third rectangle, it's going from 6 to 8. The midpoint between 6 and 8 is 7. So if I go up to 7, the height of that function looks like it's about right there. And so we'll draw our rectangle going straight across there. So how do we find the area here? Well, in this case, because these definitely don't look like nice integer values, so we're going to definitely want to use the function here and think about what x values determined the height of the function. So in this case, first, we know the width of each rectangle is 2. And here, for our first rectangle, we see that it's determined by the height of the function when x was 3. So we're going to say 2 times f of 3 plus 2 times the height of this function, height of this rectangle is what the function height was when x equals 5. So 2 times f of 5. And then our last one was, last rectangle was the height when the function, when x was 7. So 2 times f of 7. And so in this case, again, we're going to want to use our calculators in order to estimate this, or maybe it's a no calculator problem and you've got to plug them actually in. But we're going to use the actual function here to do that. Sometimes it's easier to estimate and say that this is 2 times, or not estimate, to factor, and say that this is 2 times f of 3 plus f of 5 plus f of 7. And our equation here was, I'll just write 4x minus 1/2 x squared. So this was our equation here. This is going to be equal to 2 times the function at 3. So 2 times 4 times 3 minus, actually 4 times 3 minus 1/2 times 3 squared plus f of 5. So that's going to be 4 times 5 minus 1/2 times 5 squared plus 4 times 7 minus 1/2 times 7 squared. So if I needed to write all of that out, that's what that would be. Essentially, I'm plugging 3 and 5 and 7 into our equation that they gave us here, and then simplifying. So if I have a calculator, I would use it. If it's a no calculator section, I would obviously do this by hand. But altogether for this problem, you end up getting 37 as that estimate. Now, and 37 units squared. So for this estimate, interesting here, We had 40 units squared when we did left, we did 28 when we were right, and then now we're at 37 in the midpoint. You might think that the midpoint was exactly between the left and the right, but it actually is not the case. And that's interesting to think about. All right, trapezoid sum. All right, so first off, I'm going to lead with this idea. Let me try to box this out so we've still got some room. I'm going to lead with this idea that the trapezoid sum, this is by far the most accurate. It is the most accurate one out of all of these. Given the same number of rectangles or trapezoids, you're going to get the best estimate using a trapezoidal sum. And let's sort of talk about why. In this case, we're still going from 2 to 8. So if we draw those lines, we've got x equals 2, 8 is over here. Still trying to find this area under the curve. If we're doing 3 subintervals, the width is still going to be 2. So I'll draw my lines at 4 and 6, and we've already got 8 there. Now, how can we make this a trapezoid? Instead of having these like flat lines that go across, like we do with the rectangle method, what I can actually do is I can connect the left and the right sides together, and that would create a trapezoid. So I'm going to connect this. This would be my first trapezoid. If I connect these two, that's my second trapezoid. I'm going to do one all the way going down there. That's my third trapezoid. Technically a triangle, but a triangle is sort of a special type of trapezoid where the base is 0, or one of the bases is 0. Does that blow your mind? Okay, so let's think about this. How could this be a trapezoid? How is this possible? Mr. Bortnick just drew these lines here and then drew this here. What makes this a trapezoid? Let's take a look at this shape at 1. If I sort of draw it over here, here's sort of zoomed out, or not even zoomed out, it's maybe zoomed in. In this case, you might notice that both of these are vertical lines. So they are in fact parallel to each other, which we said is really important if you're working with a trapezoid, that needs to be true. And the base is perpendicular in both of those. So what we actually have for this shape here is that we could consider this our base 1, we can consider this our base 2, and we can actually consider that our height. It's like a trapezoid that's on its side. So because of that, essentially what we've got here is we can use the area of a trapezoid, which we talked about earlier, but again, that's 1/2 times base 1 plus base 2 times the height. And so let's see what this would look like for this particular problem. For the first trapezoid, so I'll do trapezoid 1. The area is going to be 1/2 times base 1. So base 1 here is going to be the height of the function at 2. So f of 2. The second base is going to be the height of this line, right? So one base is here, one base is here. So it's the height of the function at 4. And then the distance between those is what we call the height in this formula. So that's going from 2 to 4. That's going to be 2. So times 2. That's our first trapezoid. Our second trapezoid, we're going to add the area to that. And in this case, for our second trapezoid, the bases are the height at 4 and at 6. So we're going to say 1/2 times f of 4 plus f of 6. And then the distance between those two bases is 2, aka the width, really, in this case. And then our last one, I'll do the third one here. So the third one is going to be 1/2 times the height of the function at 6 and at 8. Those are our two bases. We know f of 8 is 0, but I'm going to do it anyway for completion purpose. So f of 6 plus f of 8 times 2. So here in this case, we can go a couple of different ways about solving this. But sometimes in these problems, maybe they'll give you a table. Maybe they'll give you, clear functions you can see. But, if they give you an equation, you're probably going to have to plug those values in. Maybe use the table feature on your calculator to find those exact values and work from there. But one thing that I would say that's sort of interesting is that once we've got this written out, we actually have 1/2s in each of these. And we have 2's, which is the width of our trapezoids here. So we could actually simplify this by factoring. So simplify by factoring. And so we can pull a 1/2 out. We pulled the 1/2 out. We pulled the 2 out. What's left over? Well, we've got f of 2, f of 4. Those are from here. And then we've got another f of 4 and an f of 6. So f of 4 and f of 6. And then we've got another f of 6 and an f of 8. So plus another f of 6 and an f of 8. Well, how can I simplify this even further? Well, since I'm simplifying, I notice that both of these are the same, that there are 2 f of 4s and 2 f of 6s. So a way that I can write this very compactly is that this is 1/2 times 2 times f of 2 plus there are 2 f of 4s plus 2 f of 6s plus f of 8. This is about as factored as it can get. And for some classes, if you're curious to think about a faster way instead of writing out each area of each trapezoid, this is actually a really nice way to do it, because what we notice here is that this 1/2 is always here because of the equation for the trapezoid, right? The equation of the trapezoid always has that 1/2, but the 2 is just the width. It's the width of each trapezoid. And then you'll notice then it starts, the interval here is going from 2 to 8. It starts at 2, it ends at 8, and it's going to go up by 2 each time here. So 2, and then 4, and then 6, and then 8. It's going up by 2 each time because that was our width. In this case, though, again, like to get the answer, to go like sort of the last step, I would plug these values into my calculator and actually do that. For the check for you, you should be getting 34 when you do that, 34 units squared for this particular one. But again, I would plug those values into the equation. I would use my calculator probably in order to do that. Now, fun fact and interesting thing here is we said that 37 was not the middle between the two of these, but 34 is. That's interesting. 34 is halfway between 40 and 28. Very interesting. So the trapezoidal sum, using these trapezoids, actually just gives us the value that's halfway between your left Riemann sum and your right Riemann sum. That could be useful information to know. All right, let's keep going. How do you determine whether it's going to be an underestimate or an overestimate? Super common AP exam question. They might ask you to find those estimates, whether it's a left, right, midpoint, or trapezoidal sum. But they might ask you also, is it an overestimate or an underestimate? And really the easiest way for you to do it is to think about whether the function is increasing or decreasing. That is going to determine really everything on whether that left and right Riemann sum is above or below. If I have an increasing function and I have a left Riemann sum, notice that when you draw the rectangles using the left side, that those rectangles are going to be below. So this gives us an underestimate. But in that same increasing function, if we use the right Riemann sums, if I use the right side, notice that each of these rectangles is now above the curve, and so this is an overestimate. So if I did a Riemann sum in this case, it would be under the actual value of the area under the curve. If I did these rectangles here, a right Riemann sum, the area would be above the real area under the curve, so it's an overestimate. But these actually flip when I go from increasing functions to decreasing functions. Check it out. If I do a left Riemann sum on this decreasing function, notice now that these rectangles are above. So this is an overestimate. While if I do right Riemann sums, notice now that these rectangles are below. So that gives us an underestimate. So when you are determining whether a function, whether a Riemann sum is an overestimate or an underestimate, it is like really important for you to identify whether the function is increasing or decreasing on the interval that you're working with. Generally, your explanation on the AP exam is going to really bring that fact into account. Similarly, if we're talking about trapezoids, right? This is really for left and right Riemann sums. If we're talking about trapezoids, if I have something that, in this case, concavity is like really huge, whether it's concave up or concave down, because if we draw, I'll just draw sort of like a big trapezoid, but here's a trapezoid right here. Notice that trapezoid, the top of that trapezoid is going above the curve because this function is concave down, it's curving downwards, and the top of that trapezoid should be a straight line. It's not exactly a straight line, but you can imagine hopefully it's a straight line. So because of that, when a function is concave up, trapezoid estimations give a overestimate because it's above that curve. And if we do the same idea, if we go say from here to here, give me a trapezoid there on a function that's concave down, that's going to be an underestimate. So we're going to have an underestimate for that. So again, sort of key idea for this part, if you are talking about left and right Riemann sums, you want to figure out whether it's over an estimate or an underestimate. You need to look whether it's increasing or decreasing. That function is increasing or decreasing. If you're looking at trapezoid estimation, concavity is your friend. Is it curving upward or curving downward? That's going to help you figure out whether that function or whether that trapezoid estimation is an overestimate or an underestimate. All right. So we're on our last problem here. Now, a common AP exam style question, other than just giving a function, is to do the same things that we've been talking about, but with a table. Right? They don't give you a graph, they don't give you an equation, they just give you a table. And actually, this is my favorite application of this because you don't really need to think about the functions, you're just using the values that are here. So let's see what we've got. The rate at which water is being pumped into a tank is given by the continuous and increasing function r of t. Table of selected values of r of t for the time interval from 0 to 12 minutes is given below. So we can see the time looks like each of these is being separated by 3 minutes. And then r of t is a rate. That's important to notice. It's in gallons per minute. So they said the rate at which the water is being pumped into the tank is given. Okay, so use the following Riemann sums with the given intervals to estimate the number of gallons of water pumped into the tank during the 12 minutes. If they asked us to find a right Riemann sum with 4 subintervals, we're going from 0 to 12, right, during the 12 minutes. In this case, optimally, if we're thinking about it, what would the width be? Well, the width would be, we're going from 0 to 12, so 12 minus 0, and we have 4 subintervals. So that's 12 over 4, which is 3. And we notice that each of these is, in fact, increasing by 3. Now, this is not always going to be the case. Sometimes you don't have the same amount of width each time, and you would need to take that into account. But what we're going to imagine here is we have our right Riemann sum, and so we would have a rectangle going from 0 to 3. Now, if I'm doing a right Riemann sum, that means that I'm going to use the height of the function on the right side, which is here at 3. So that's going to be 13, height of 13 here. So the first rectangle is going to be 3 for the width times a height of 13. For my second rectangle, I'm going from 3 to 6. The right side of that interval is at 6, so I'm going to use the height of the function there, which is 18. So 3 times 18. For my third rectangle, going from 6 to 9, I would need to use the right side, the height of the function when t is 9, so that's going to be 23. So that's 3 times 23. And then for our last rectangle, the height of the function on the right side when t is 12 is 27. So 3 times 27. So this is the same thing as 3 times 3 plus 18 plus 23 plus 27. I just factored that 3 out. So that's going to be what? 3 times 81. And so that's going to be 273 gallons. So 273 gallons. It gets pumped out of that tank in that 12-minute period between t equals 0 and t equals 12. And again, so that was our right Riemann sum way. Again, recap. I imagined essentially rectangles going from those intervals, and I used the height on the right side of each one. So that's why I used 13, 18, 23, and 27. And I didn't use 7 because that's on the left side. Interesting. Same idea, though, if we want to do left Riemann sums with 4 subintervals. Okay, the width between each one is still going to be 3 because we're doing the same number of subintervals as the last time. And if we're using the left side, the first rectangle is going from 0 to 3. The left side is 0, and the height of the function is 7 there. So the width is 3, the height of 7. For our second rectangle, going from t equals 3 to t equals 6, the left side of that is at 3, and the height of the function is 13 there. So 3 times 13. For the third rectangle, going from 6 to 9, we're going to use the left side. So the height of the function is 18 when t equals 6. So 3 times 18. And then going from 9 to 12, we're going to use the left side again. The height of the function is 23 when t equals 9. So 3 times 23. So if I factor that 3 out, that's 3 times 7 plus 13 plus 18 plus 23. Altogether, that's going to be 3 times 61, which is going to be 183 gallons if we do that. So one estimate is 183 gallons were pumped out. The other estimate is 273. We got to assume that the answer is somewhere between these, but those are pretty broad differences. That's almost 100 units, 100 gallons difference between these two. In the right Riemann sum, is the approximation greater or less than the true value, and why? Well, in this case, remember that if we're talking about Riemann sums and we're talking about approximations being greater or less than, we care whether the function is increasing or decreasing. They told us here that the function is actually increasing. It's an increasing function. And if I ever forget, we know that the function is increasing. What I'll do is I'll just draw a little increasing function. And if I draw my right Riemann sums, I can remember that my right Riemann sums are above. So I would say in this case it is an overestimate since, and here's our reasoning here, r of t is increasing and we're doing a right Riemann sum. And we're doing right Riemann sum. Similarly, for this one, if we do a left approximation, maybe I could do that over here. If we draw a little increasing function that we've got right here and we do a left, notice that if we draw those rectangles on the left, that they're going to be below that curve. So our answer for this, for the left Riemann sum, is we're going to have an underestimate. And the reason is still because r of t is increasing and we're trying to find left Riemann sums. So that's what the justification for this looks like. The midpoint Riemann sum with 2 subintervals. Okay, here when we're doing 2 subintervals, we're going from 0 to 12, and we're only doing 2, so that's going to be 12 over 2, which is a width of 6. How do we do this with this table? Well, I'm going to erase the intervals that we've got here. Essentially, if the width is 6 and we're going from 0 to 12, we have one rectangle going from 0 to 6, and then another rectangle going from 6 to 12. The midpoint means that we need to use the height of the function halfway between those x values, or t values in this case. So halfway between 0 and 6 is 3. So I'm going to actually use 13 as the height for that first rectangle. And then halfway between 6 and 12, the midpoint of those is 9. So I'm going to use the height of the function there, which is 23. The width of the rectangles we're talking about is 6. The height of that first one is 13. The second rectangle goes from 6 to 12. That's 6 units wide. And the height of that rectangle is going to be 23. So this estimate with 2 subintervals would be 6 times 13 plus 6 times 23. That estimate would be 216 gallons for that one. And this is now the final one for this one. If we want to do trapezoidal sum with 4 subintervals, how would we do this with 4 subintervals? Well, with 4 subintervals, we know the width is 3. We actually found that originally for our Riemann, our left and right Riemann sums. So I'm going to erase what I've got up here for these. We've got 4 trapezoids. So one is going from 0 to 3, one is going from 3 to 6, one is going from 6 to 9, one is going from 9 to 12. Now, the width of the intervals is the height in this case. I'm going to use sort of our shortcut method, our factored form that we talked about way back when over here, and I'm going to show you how to do that with this table. So I'm going to start with the 1/2, because the 1/2 is part of the trapezoid sum. And you could do just 4 different calculations of area here and add those up. But me, I like the elegance of like factoring first and then doing it that way. So the 1/2 is going to be first, then the width between those two, between these values is going to be next. Because this is consistent, I can do this factoring method. If you are ever doing a table and they're not, the time or the x is not increasing by the same amount, you cannot do this shortcut that I'm about to show you. But because these are each 3, I'm going to factor the 3 out of each of these area equations. And what's that going to leave me? It's going to leave me the height of the function. So the base 1 for this first one is 7 plus 2 times the next one, which is 13, plus 2 times the next one, which is 18, plus 2 times the next one, which is 23, and then plus the last one, which is 27. So all I did for these values, 7 and 13 and 18 and 23 and 27, you might see that those came from the y values of our table. Right? Those came from right there. And why are these 2's here? Why are these 2's here, and why are they only in these middle ones? You might remember when we did this factoring form up here that the only ones that had duplicates were these center ones, and these ones on the ends didn't. So we ended up with these like extra 2's for the middle parts, while the height of the function at the ends of the trapezoids did not get the 2's. So this is the sort of nice format. If you can get some practice doing it this way, it's nicer to me because I don't like doing 4 separate trapezoid equations or area calculations. This is much nicer to me that's all in one thing. But if you do this, this is going to be about 213 gallons as our solution for this. And I would expect that that is halfway between 183 and 273, that trapezoidal sum, because we have the same number of intervals here, should be exactly half between our left and our right. That is it, and this was a long one. Shout out to you if you made it all the way through this to see these different types of Riemann sums. But as usual, we've got practice listed here, different types of practice for the left, the right, the midpoint, the trapezoid. Try it out. Check your answers on the posted answers. Come to class with any questions, and stop by office hours if you've got any questions as well. Good luck on your mastery check this week. I hope that goes well, and take care. Have a great rest of your day.